Chemistry time.
Hello and welcome back to Chemist Tea Time. In our previous discussions, we were introduced to some different types of chemical bonding and how these compounds were named. Now let's take a closer look at some calculations involving compounds including molecular mass, percent mass, empirical formula, and molecular formula. As a review, we can find the molar mass of an element using the atomic mass, and this represents the mass of 1 mole of atoms of that element. We can also use the atomic mass from the periodic table to calculate the molecular mass of compounds. By adding together the individual atomic masses of all the atoms in that compound, we can find the total molecular mass of that compound. For example, a molecule of carbon dioxide contains 1 carbon atom and 2 oxygen atoms. To find the molecular mass of CO2, we would add the atomic mass of carbon, which is 12.01 AMU, to the mass of 2 oxygen atoms, which are 16 AMU each. When we add these values together, we find that the molecular mass of CO2 is 44.01 AMU. By extension, this means that the molar mass of CO2 would be 44.01 grams per mole. This represents the mass of 1 mole of CO2 molecules. When discussing compounds, one important property that we need to be aware of is the law of definite proportions, which states that the ratio of each type of atom in a substance is the same throughout the entire substance and is unique to that compound. This means that for a compound such as carbon dioxide, so CO2, regardless of the amount of carbon dioxide we have, we will always have the same mass ratio of oxygen to carbon. This law is very useful as it allows us to calculate the exact amount of a particular component within a substance using the following formula. The fraction of a certain element within a substance, also known as the mass fraction, is equal to the mass of that component divided by the total mass of the substance. Mass fraction can also be expressed as a percent by multiplying it by 100. Assuming we had 1 mole of CO2, we would then have 27.3% carbon and 72.7% oxygen by mass. Regardless of where the sample came from or how it was prepared, every molecule of carbon dioxide has a fixed composition and will always have the same percent of carbon and oxygen. In chemistry, we have different types of chemical formulas that show the ratios in compounds. The simplest formula is the empirical formula, which is defined as the smallest whole number ratio of each element in a compound. You may find that the empirical formula for a compound does not always represent the actual makeup of a molecule. This is because the empirical formula only describes the lowest whole number ratio of atoms. In contrast, the molecular formula represents the actual number of each atom in the molecule of that compound. In some cases, such as with water and carbon monoxide, the empirical and molecular formula are the same. In other cases, the molecular formula is different, such as with hydrogen peroxide, which has the empirical formula of HO, but a molecular formula of H2O2. Note that although the number of each atom is different, the ratio is the same for both the empirical and molecular formula, but only differ by a common whole number multiple. In many cases, we can determine the empirical formula from experimental data. For example, if 100 grams of an unknown compound contains 92.2 grams of carbon and 7.8 grams of hydrogen, we could use this data to find the empirical formula by determining the ratios of carbon and hydrogen. We start off by determining the ratio of carbon atoms to hydrogen atoms, and to do this, we must convert to moles. Using the molar mass of carbon and hydrogen from the periodic table, we can determine that we have 7.68 moles of carbon and 7.7 moles of hydrogen. The final step is to determine the empirical formula by finding the ratio between the two elements. We can then find the ratio of carbon to hydrogen by dividing by the moles of hydrogen, which is the larger value, by moles of carbon. The ratio is approximately 1 to 1, therefore our empirical formula is CH. In some cases, we may need to round this ratio to the nearest whole number because we can't have fractions of atoms, and we are using experimental data, not exact values, or multiply it by a number to get a whole number. For example, if you have a fraction of 0.5, you would multiply everything by 2 to get a whole number. Because the empirical formula and molecular formula only differ by a whole number, if you were provided the molar mass of your unknown compound, you could determine the molecular formula by finding the ratio of the empirical formula mass to the molar mass. Continuing on with the same example, if this molecule has a molecular mass of 78.1 grams per mole, what is the molecular formula? First, you will need to calculate the mass of the empirical formula, which is 13.02 grams per mole. To find this whole number ratio, we divide the molecular mass by the empirical mass to get a value of 6. We then multiply every atom in the empirical formula by this value, and we get a molecular formula of C6H6. Combustion analysis is another common way to determine molecular and empirical formulas for unknown compounds that contain carbon and hydrogen along with other elements. An important component of this is the law of conservation of mass, which states that matter cannot be created nor destroyed, it can only change forms. This means that if we start off with a certain mass of an element, such as carbon, that same mass of carbon must be present at the end of the chemical reaction. In combustion analysis, a known mass of the unknown compound is burned in excess oxygen to produce CO2, water, and other products based on composition. By measuring the mass of these products, we can determine the masses of each element in the unknown compound and the empirical and molecular formula. For example, if 2 grams of a compound containing carbon, hydrogen, and oxygen is burned, it produces 3.82 grams of CO2 and 2.35 grams of water, we can use this information to find the empirical formula. We can use the mass of CO2 and water to determine the starting amounts of carbon and hydrogen respectively. We can use the molar masses to convert the mass of CO2 into moles of CO2 molecules. We also know that 1 mole of CO2 contains exactly 1 mole of carbon atoms. This means that the products contain 0.0868 moles of carbon atoms in the unknown compound. We do these same steps for hydrogen, noting that there are 2 moles of hydrogen atoms in every 1 mole of water molecules, and we find that there are 0.261 moles of hydrogen atoms in our unknown. Oxygen is a little bit more complex because it is in both products, so an easy way to determine the amount of oxygen is to find the difference in mass between the unknown and the mass of carbon and hydrogen. 0.0868 moles of carbon atoms has a mass of 1.04 grams of carbon, and 0.261 moles of hydrogen atoms have a mass of 0.264 grams of hydrogen. Since the unknown has a mass of 2 grams and only contains carbon, hydrogen, and oxygen, then the remaining 0.70 grams must be made up of oxygen. Using the molar mass from the periodic table, we find that this mass of oxygen represents 0.044 moles of oxygen atoms. Now that we have the amount of each element in moles, all that's left is to determine the ratio to find the empirical formula by dividing everything by the smallest number of moles, which is oxygen. This then gives us an empirical formula of C2H6O. I know we covered a lot of different types of calculations today, but it is important that you practice and understand the steps involved in each. As a review, we showed how to determine molecular mass, percent mass, empirical and molecular formulas for all different types of compounds. Make sure you join us next time and have a wonderful day. Thank you.